for this program is provided by Annenberg CPD to advance excellent teaching.
At this point, we've learned a lot about electricity. We know about forces and charges and voltages and electric currents and so on. And the question arises, what's all that about? What's really important about all that stuff? Let me give you an example of what I mean. Remember von Maurer's giant machine that he had made for him at the end of the 18th century. It could develop a voltage of 100,000 volts. It used a bank of 100 Leyden jars to store energy in, and it could store 2,000 joules of energy. And so the question is that impressive? And the answer is really no. 2,000 joules of energy is about 1/2 of one food calorie. Or to put it in purely electrical terms, this little 9-volt transistor radio battery can store 10 times as much electrical energy as von Maurer's bank of 100 Leyden jars. And yet, that machine could hurl a lightning bolt a distance of 2 feet, and the battery certainly can't do that. And so the question is, what really is important? What matters? Voltage, or electric potential, is a measure of the potential energy of an electric charge, such as, for example, the electrons that make up the atoms in your body. And so you might ask the question, what is the potential binding electrons to your body? It had better be much more than the potential that I can develop by cranking up that machine, because if it isn't, the machine would be devastatingly dangerous. It could rip all of us to shreds. And so, is it true that electrons are bound to your body much more strongly than I can develop a potential with that machine? The answer is no. The binding potential of an electron in your body is only a few volts, 3, 4, 5 volts. I can develop 100,000 volts by cranking up that machine. And so once again, we're left with confusion about what's important in electricity. The basic elements of electricity are very simple. If I can imagine point electrical charges in a vacuum, then there are positive charges and there are negative charges, and they attract each other or they repel each other with a force that varies inversely as the square of the distance between them. And that's really all there is to it. And yet it took thousands of years to figure that out, and even today when we understand it very well, it's still confusing and difficult to learn about. Why is that true? Well, the reason it's true is because these elements of electricity, point charges in a vacuum, never exist in the real world. Electricity always exists in matter. And so in order to understand electricity, we must first understand matter. But matter is essentially electrical in nature. And so in order to understand matter, we must first understand electricity. And that's the crux of the dilemma that we want to speak about today.
first glance, trying to see electricity in its true light seems as risky as a night out on the Las Vegas Strip. Electricity has numerous quantities: charge, potential, and field, to name a few. And with such a bewildering variety, it's hard to know which quantity to bet on. What's needed is a way to explain how everything fits together. A way to stack the deck in favor of good sense and clarity. What's needed is a surefire method behind this madness, the cause behind the effect of electricity. What's needed is a change of scene. On the surface, the electrical connection between Las Vegas and these Nevada hills isn't immediately obvious. For one thing, surveyors don't gamble. There's nothing random in the detailed precision of their maps, nor in their measurements that determine the height above sea level of each point on a predetermined grid. A line is drawn, connecting all points a certain height above sea level, and then repeated for other heights at regular intervals. To a practiced eye, the resulting contours of constant height give a clear representation of the real landscape. By the same token, the contours on this map give a clear representation of an electric field. These are contours of constant electric potential, and they too represent a terrain that has its ups and downs. When real ground goes up and down, the prudent traveler wants to know about it, because going uphill can be hard work. And exactly the same is true for electric potential. Moving up the incline of potential is hard work. And the steeper it is, the harder it is to climb. Of course, if the potential isn't changing, it takes no work at all. And if the potential decreases, the field is downhill all the way. In this analogy, electric potential is elevation, and electric field is the downward slope. To put it in more mathematical terms, the electric field is a negative derivative of the potential. Or, in other words, the potential is minus the integral of the electric field. The electric field of a single point charge is proportional to 1 over r squared. So its integral is proportional to 1 over r. For a single point charge, the direction of the field is pretty obvious. But what about more complicated situations? What does the electric field for this potential look like? Because it takes no work to move a charge along a curve of constant potential. There's no component of field in that direction. So the field is perpendicular to each equipotential at every point. And that's how it assumes its familiar shape. familiar shape of even the most rugged terrain isn't all peaks and valleys. Some regions are perfectly flat and horizontal. A lake is a region of constant height above sea level. Just as a region of constant electric potential is created by a conductor in an electric field. And since electric potential is the same everywhere on the surface of a metal, the electric field is always perpendicular to that surface. Out in the hills, it's hard to find much that's perpendicular to anything, but in the city, it's easy. And here it's easy to find electricity at work and at play. Although this proliferation of light and color is probably not what the pioneers of electricity had in mind, they nevertheless laid the foundation for it. Ben Franklin did his part by bringing electric potential out of the heavens and down to earth. Thomas Edison, thinking more about work than play, captured electricity in glass and made it yield light. The eventual proliferation of neon signs was probably not even imagined by Georges Claude, the French physicist who developed a practical neon light in 1909. Those first neon lights were put to work in the Grand Palais in Paris, not as decoration, but as house lights. The reddish glow of those lights was seen as a drawback by everyone. Everyone but Jacques Fonseca, a publicist. In that red glow, he saw great possibilities. He persuaded Claude to sell him the rights, and by 1912, Paris had the world's first neon sign, and the work had barely begun. Electric potential is the ability to do work by making electric charges flow. And no matter where they go, their potential is measured in volts. But how big is a volt? And how many volts does it take to do a job? A flashlight battery is rated at 1.5 volts. With only 2 of them, one can do work worth millions. When necessary, 12 volts is enough to start the getaway car. And 110 volts enough to light a bulb or two, or send a crook fleeing into the night. However, crime doesn't pay. Even with a one-armed bandit, the game can go too far. When that happens, nobody wins. On August 6, 1890, at 6:40 a.m., at Auburn State Prison, New York, Mr. William Kemmler was the first person in the world to die by electrocution. It took approximately 17 seconds and several thousand volts. But the electric chair wasn't the first use of high voltage. In the 18th century, Van Marum's giant electrostatic generator could generate 100,000 volts. So could the smaller Wimshurst machine and the Van de Graaff generator. And in the modern physics laboratory, this tandem Van de Graaff particle accelerator uses 3 million volts. But high voltages are not confined to exotic laboratories. Every day, power lines carry electricity at hundreds of thousands of volts across the land toward the city, where neon lights use about 10,000 volts to do their work. And part of that work is to hold this town together. Occasionally, they even help bind people together. But electricity is also responsible for an altogether different type of binding. The atom itself, the basic building block of everything we see, feel, or smell, is held together by the force of electricity. And that bond between the electron and the atom has a definite voltage. That voltage holds the world together. And so what is the voltage of the atom itself? In every atom, the electric force binds negatively charged electrons to a positive nucleus. The nucleus is so small, it can be thought of as a point positive charge, even though it really consists of neutrally charged neutrons and positively charged protons. Each electron has exactly enough negative charge to balance the positive charge of one proton. The result may be a perfectly neutral atom. This picture, or any picture of an atom, is only a model. But as a model, it is a guide to fact. And one such fact of great importance is that the distance from the nucleus to the outermost electron of any atom is always about 1 angstrom unit, 100 millionth of a centimeter. From the point of view of that outermost electron, the other electrons virtually balance the electric charge of all the protons in the nucleus except one. So, the outermost electron detects very nearly the electric field and the electric potential due to one proton, about an angstrom away. Its electric potential works out to just a few volts. And because its charge is negative, so is its potential energy, conveniently measured in units called electron volts. Those few electron volts, minus a little kinetic energy, is what has to be overcome to tear an electron from an atom. About the same is needed to remove an electron from a molecule, or from a hunk of solid metal. Considerably less has to be overcome to tear dollars away from Las Vegas tourists. While the gambler's attraction for money is great, the bond between any $1 and the gambler is very slight indeed. But some of the other bonds made here are more long-lasting in nature. At least in some cases, the tie is very strong. But when a few volts tie an electron to an atom, how strong is that bond? Since a Van de Graaff generator can build up 100,000 volts, it seems this machine ought to be capable of ionizing every bit of ordinary matter in sight. But it isn't. Sometimes, voltage alone isn't enough. In fact, if an atom and a Van de Graaff engage in a simple tug-of-war for one electron, the atom always wins. Because the tug-of-war is a question of force, not voltage. In other words, what matters is the derivative of the potential energy, not just how big it is. Here's the Van de Graaff dome and an atom. They're competing for an electron that might be bound to the Van de Graaff by tens of thousands of volts. But zooming in by 10, 100, 1,000 times, the electron's potential energy due to the atom is seen to be much smaller, but very much steeper. In fact, the horizontal scale has to be expanded 10, 100, 1,000, 10,000, 100,000 times just to see the slope. The atom's force is 100,000 times stronger than the Van de Graaff, and that's no contest at all. And it's not much of a contest when the house determines the odds. That's why the smart players prefer to leave little to chance. Benjamin Franklin was such a person. He even found a way to take some of the risk out of thunderstorms. And in fact, his invention of the lightning rod spared many a church, barn, and home from flaming destruction. Where does the light and lightning come from? As in any spark, the molecules of air are momentarily ionized, leaving a gas of positive molecular ions and negative electrons, called a plasma. Very quickly, the electric force between ions and electrons causes them to recombine into neutral matter, giving off their excess energy in the form of light. But lightning can be tamed. In a neon tube, for instance, the same process can be slowed to a continuous glow. But the electric field in a neon sign, or a Van de Graaff machine, or even a storm cloud, can't ionize matter. So how do they cause sparks to fly? The answer is that they do ionize the air, but not in a direct tug of war. The air around the Van de Graaff bulb always contains a few accidental electrons. The electric field of the Van de Graaff accelerates such an electron until it hits another molecule. Then it starts over again. If the distance between atoms is large enough, and the field is strong enough, the electron can build up enough kinetic energy to knock another electron off when it hits. If that happens, both are accelerated, causing more ionization in a chain reaction that creates a spark. So, a Van de Graaff machine or a neon sign ionizes the air not by sheer electric force, but by collisions. While that's not exactly cheating, it's a trick nonetheless. But then, this town's full of tricks. Tricks of the trade, scientifically designed to ionize the tourists' pocketbooks. It's also full of energy, and the energy of the people seems to rise by the hour. Electric energy, on the other hand, goes up with voltage and with charge. So, the question of how much energy an electric device can deliver depends not only on its voltage, but also on how much charge it has available. The Van de Graaff and this giant electrostatic generator both reach very high voltages before sparks discharge them. But even Van Marum's 100 Leyden jars couldn't store nearly as much charge as there is in an automobile battery. Even though it has a far lower voltage than those machines, it stores so much charge in chemical form that it's vastly more useful. In fact, a common radio battery stores 10 times the energy of Van Marum's generator. A battery is a storehouse of energy, but on any given day, despite any given number of batteries, much more energy is actually stored right here. Yet only a small fraction of this water's vast potential energy is converted to electrical energy. That energy travels across the desert, to the city, where it's radiated into the night in all colors, shapes, and sizes. But behind the glittering facade, charge and field, energy, voltage, and force are the stuff of electricity. And that's the stuff that holds the universe together.
At the beginning of the 1800s, a British chemist named John Dalton proposed the law of simple and multiple proportions. And that law, for the first time, gave a solid scientific foundation to the ancient idea of the atomic theory of matter. But not all scientists accepted Dalton's theory. Throughout the century, there was a group of conservative chemists who essentially thought that it was bad science to believe in anything that you couldn't see. Of the atomic theory, they said, we don't need that hypothesis. And they weren't the only ones who didn't believe in Dalton's theory. Dalton had a rival for the title of greatest chemist in England, and his name was Humphrey Davy. And Davy didn't believe in Dalton's theory either, but his reason was the exact opposite. He thought that Dalton hadn't gone far enough. His argument went something like this. He said, look, there are 40 chemical elements that we know of. That means that according to Dalton's theory, there must be 40 different kinds of indivisible atoms to explain the properties of those elements. But, he said, of those 40 elements, 26 are metals. They all share the same properties of shiny surfaces and good electrical and thermal conductivity and mechanical ductility and other properties. Now, he said, those can't be accidents that just happen 26 separate times. There must be some underlying principle of metallization. That is to say, Dalton's atoms must have some inner structure. Well, it took 100 years, but it turned out, in the end, that both Dalton and Davy were right. Matter is made of atoms, and atoms do have an inner structure which explain why metals exist. But long before that was understood, in fact, even before the time of Davy and Dalton, all of it was made use of by a wily Italian named Alessandro Volta, who invented the electric battery. And that's our story for next time.
Funding for this program is provided by Annenberg CPD to advance excellent teaching. For information about this and other Annenberg CPD programs, call 1-800-LEARNER and visit us at www.learner.org.